Elastic potential energy and simple harmonic motion 4.5. So you have seen spring. So if there is no force applied on a spring, it is neutrally just resting. And the position of that, we call it x0. When you apply force and you stretch that to the right, you're holding this, but you feel the force. You feel that this spring is forcing your hand into the left. So spring is resisting to the force that you're applying. That's why when you want to talk about the force that the spring exert on the object, it is negative kx. This negative is because the force of the spring always is against the movement of the spring. Here the spring is moved to the right. Now the force exerted by the spring is onto the left. The force of the spring is equal to negative kx. K is a spring constant. It depends on the physical property of the spring. The more tougher or more thicker is the spring, is harder to compress or stretch. X is a displacement of the spring. Let's say here, neutral it is at 0. Then you exert a force, you displace it by X. So X is displacement of a spring. Okay, let's just look at this question. A student stretches a spring horizontally at distance 50 millimeter. You need to convert millimeter to centimeter. Applying the force of the 0.18 Newton east. Determine the force constant of the spring. Knowing the force is kx, you rearrange for k. K is the force divided by x. Force is 0.18 given, and x you just convert it into the meter, 0.015. You just k 12 Newton per meter. So k is Newton per meter, is F over x. The unit for F is Newton, X is meter. That's why the unit of K is Newton per meter. What is the force exerted by a spring on students? So the force exerted by is opposite. If this is to the east, that one is going to be to the west. Here is another question. A ball of mass 0.075 is hanging from a vertical spring that is allowed to stretch slowly from its under tertiary equilibrium position until it comes to a new equilibrium position of 0.15 below its initial one. Is the system diagram substitution depicted? Determine the force constant of the spring. Since without attaching any object, originally the spring was at x equals 0. So nothing is attached into the spring like that. So your spring end is here. But when you attach an object, of course, it will stretch it out. The thing is that we want to find the force constant of the spring. We know this is an equilibrium, it's not moving. So total forces in y direction is 0. So what are the forces here? We have kind of the force of a spring that is pulling the object up, is negative kx, and the mass of the object mg. These two need to be equal or cancel each other. You see mg plus negative kx is 0. You just rearrange it for k. You get k to be 4.9. The m mass is given, g is 9.8, x displacement is given to be 0.15 meter. Now, if the ball is returned to its spring on a stretch equilibrium position and then allowed to fall, what is the net force on a ball when it dropped 0.075? Now, here you attach that here, so it's come down by itself, right? So actually it moves. So Then the ball position, let's say, is here, 0.071 from the equilibrium. I want to see what is the net force here. Of course, we'll have some acceleration here. There will be net force there. So not going to be zero. Again, we have a kx and we have mg, but they won't cancel each other. Here, total force in, here we call it y direction, right? This mg minus negative kx. So m we have, g we have, k we got it from the previous state, the steps x is given. You see the net force is not zero, it's 0.39. We can find the acceleration. So the next part is to determine the acceleration of the ball. You know, total force is equal to ma. Just rearrange for acceleration. Total force we got it from previous step divided by m mass of the ball. This is the acceleration. So you can do question number 3 and 4. Here, question number 5 you can do. Elastic potential energy. So we know this area under force displacement diagram will give you the energy. So if this line represents the kx, so the equation is like that. F is equal to kx. So the slope of this line is k. So this is the y component, which is your f, which is the kx. And here, from here to here is x. So area is going to be kx multiplied by x divided by 2. If you do it, it's going to be half kx2. So the energy of elastic energy, potential energy stored in a spring by stretching or compressing is going to be half kx power 2. This is the question. An apple of mass 0.1 kilogram is attached to a vertical spring with a force constant 9.6. The apple is held so that a spring is at its stretch equilibrium position. Then it's allowed to fall. Neglect the mass of the spring and its kinetic energy. How much elastic potential energy is stored in spring when apple has fallen 11 centimeters? So when it's not falling, the x is 0. When it's fall, it's 11. You know, the equation of elastic energy is half kx2. This energy is stored in it. K is given, x is 11 centimeters. Turn it to the meter, and then you calculate the energy into the joule. Part B said, what is the speed of the apple when it has fallen 11 centimeters? Conservation of the energy we can use. So here we have a potential energy of the gravitational potential energy. We have the speed here is kind of 0. Here when it's reached there, we have gravitational potential energy, we have energy stored in it, and we have a kinetic energy. So looking at that, when the apple is at equilibrium, we put that to be let me just go back to the picture. Here on the first position, we assume that here is kind of the edge here, right? So this point will have some gravitational potential energy. So it's just mgh, right? So it's E of gravity is mgh. Just hide some distance. Let's say we can now put our zero potential of the gravitational field anywhere we want, right? I choose that to be here. So here velocity is 0 because you're just holding that up. And it is on a stretched position, right? So Velocity here is just ek is 0. Also E of a spring, that is half kx2, x is 0, so it's 0 here. When it's there, my E of G is 0 because it's now on my 0 potential energy. I decided to be here, gravitational potential energy. But since it's stretched, I have E of spring half kx2, right? X is 11. And I have some velocity because it's just trying to drop. E of kinetic, I have half mv2. So conservation of energy is saying that energy here, which is mgh, is equal to addition of energy here is equal to half kx2 plus half mv2. We have x, we have h here is 11, we have mg, or we have m here. The only unknown is velocity. We just established that conservation of energy equations, as you see there. Then we can rearrange for velocity and just you get the velocity you want me to the second. So here is another question. A group of students practicing initial spring walk contest is given a spring and the following challenge. Launch the spring so that leaves the launching pad at an angle of 32.5. That's a picture. Above the horizontal and strike the target at the same elevation. A horizontal distance 3.65. Friction is neglected. So what is measurement? What measurements must the student make before they perform their calculation and launch their spring? Okay, we need to, as a spring is a stretch, we need to have that, right? According to law of conservation energy, the spring is released, this energy conserved into kinetic energy. The spring then move as a projectile, converting the horizontal range given by that. So this equation we got it from the previous unit. And you have a projectile motion, so this is coming like projected and land there, right? So here, all of this is when you just compress the spring, it's the energy turning to the potential energy. And when you release it at this end, completely turn to the kinetic energy. And then the range that is going as a projectile motion, the delta x of that will be given by that equation. Right? So calculate the stretch needed for a spring to reach the target if the spring's mass is 15.4 grams and the force constant is given 28.5. Now, just having this, the delta x equal to v power 2g sine 2 theta, this is for projectile motion. Knowing the x, knowing the g and theta, we can find the velocity. Having the velocity, conservation of the energy, all kinetic is all potential turn to the kinetic. We have a velocity is launched from this part. We have mass, we have k. We can calculate how much is spring to be compressed. So the practice, we can do question 8, 9, 10, 11, 12, 13, and 15. This is page 211. So here is now We want to talk about simple harmonic motion. When this simple harmonic motion, so you compress or you stretch the spring and then let it go. When it let it go, it will oscillate back and forth around the equilibrium. You stretch it, you let it go, so it go back and completely compress, and then again this oscillation will continue if there is no friction. So the period of this oscillation is equal to pi, square root of mass of the object is attached divided by the spring constant. Knowing that T is 1 over F, T is 1 over F, or F is 1 over T. So for frequency of that motion is 1 over 2 pi square root of K or N. Here, an example is 0.45 kilogram mass is attached to a spring with a force constant. The mass spring system is placed horizontally with a mass resting on a surface that has negligible friction. The mass is displaced 15 centimeters and then released. Determine the period and frequency. Okay, knowing that the period is 2 pi mass over K, the mass is given, K is given, you can find the period. The frequency is going to be 1 over period simply. We can practice question number 17 here, 18 and 19. Now, we can talk about each position because energy is conserved, of course. At different the energy is converted from one form to another form. For example, at equilibrium, we have a zero elastic potential energy because no stress. X is 0, half kx2. X is 0 means this is 0. Elastic energy is 0. Potential energy here is 0. So it means it's purely velocity. So you have maximum velocity there. Then as it is stretched, this velocity will turn into the potential. At a moment it is stopped, so the velocity is 0, means kinetic energy is 0, and all of the kinetic energy is turning into the potential energy. It means at this end, you have maximum potential energy. Let it go back again, all the potential is turned to the velocity. Here you have maximum velocity, then it's compressed. Fully compressed, it stops, so its velocity is 0. It means kinetic energy is 0, and everything is turned into the potential energy. So you have a maximum potential energy. There. This is a maximum stretch here and maximum compress here. Any point between these will have a kinetic and potential energy. We can use the conservation of energy at any point to establish those equations. See, there is a question. A 55-gram box is attached to a horizontal spring. Force constant is given. The spring is then compressed at position 8.6. So this is a maximum compression. Box is released and undergoes simple harmonic motion. What is the speed of the box when it is at position x 5.1 from the equilibrium position? At this position, we have kinetic and we have potential because the maximum compresses 8.6. So it's not reaching the amplitude, right? So at this position, we have a kinetic and we have a potential. See, if I establish that, I have kinetic and I have potential. But at this point, when it's completely compressing, there's just all potential. We don't have any kinetic. Here is 0. We have potential is Ka2 divided by 2. I can rearrange for the velocity here. And I have everything, so I can find the velocity. What is the maximum speed of the box? The speed of the box is maximum when is at equilibrium x is 0, right? So when you establish this equation, I know Ka2, this is equal to half mv2. Let's say at the point is fully compressed is here, and at the point that x equal to 0, right? At this point is fully compressed. The energy is Ka2 divided by 2. We don't have any kinetic here. It should be equal to energy here. Energy here, we don't have potential, it's all kinetic, half mv2. We can rearrange the velocity. This velocity will be maximum as the square root of k a power 2 divided by m. We have k, we have a, we have mass, and this we can do. This is the maximum. They use the different points, but we can use absolutely here. Just want to show you guys there. I use this point that is fully potential and this one that is fully kinetic max. So to find the maximum velocity. So here is just elastic Ka2, Kx2, and here is half mv2. Just consider so equal these two together to find the maximum velocity. Okay, so damped harmonic motion. Damped harmonic motion, if there is a friction, of course, the amplitude will not be constant. As you see, it's getting smaller and smaller, and it will disappear. So you can do question number 23, 24, 25 practice.